Okay, so continuing the conversation about polytime reduction between problems. So here we have two problems. Tried to pick problems that are not too easy so that they get across the idea of some of the difficulties that a person can run into, but also pick problems that are not too hard so a person can have some idea what the heck is going on. So we're thinking about two different problems here, graph colorability and satisfiability. And we're going to show that graph colorability is polytime reducible to satisfiability. Okay, so just to recall what the two problems look like. So a problem is a graph is K colorable. Here, a graph is K colorable if we can partition the vertices into K many classes. The classes are called colors. It's just a word because that's how they're pictured. So there's no edge between two same colored vertices. So for example, here I am looking at a light blue vertex. Now, it's connected to a dark brown, a light brown, and another light brown vertex. The point is that this light blue vertex is not connected to any other light blue vertex. Likewise, down here is a dark brown vertex. It's connected to a whole bunch of other folks, a light blue, a light brown, and another light blue. But it's not connected to any dark brown vertices. Okay, so that makes this a perfectly good three coloring of this graph. Okay, and then of course propositional logic expression is satisfiable if there is an assignment of the values t and f to the variables that makes a statement as a whole evaluate to t, and we've been talking about that a lot, so I think that's probably very familiar. Okay, now so we have to demonstrate that graph colorable is p reducible to satisfiability, polytime reducible to satisfiability. So we're going to show that given an instance of graph colorability, you could translate it into an instance of satisfiability in such a way that the translation algorithm takes polytime. So let's go through an example. Okay, so we're going to go through the k equals 3 construction, and other k's work the same way. So we're going to write down the set of three colorable graphs as L1, and we're going to write the set of satisfiable propositional logic statements as L0. So let me try that. So let's see, how's it go again here? So I'm going to write L1 for the set of three colorable graphs. So the set of graphs that are three colorable. Now, of course, this is actually, technically, this is a representation of a graph, so we're probably representing the graph using bit strings. But so L1 is a language, a collection of, technically a collection of bit strings, and we're going to interpret those bit strings as meaning graphs, and L1 consists only of the representations for those graphs, the graphs that are three colorable. And L0 here is going to be the set of propositional logic statements. Again, representations of propositional logic statements technically. Propositional logic statements that are satisfiability. So S is a propositional logic statement. That is satisfiable. Okay. And of course, we want to show here, that L1 is p reducible to L0. And the question is, how do you do that? So we have to produce an F. F maps the set of all graphs over to the set of all propositional logic statements. And it has to have the property that if the graph G is in L1, you're looking at f of G is in L0. Okay, and again, just to have said it, just so that I feel like, a person remembers that these are, of course, strings. So technically, this is a bit string, and this is f of sigma. And of course, the F here has to have a Polytime algorithm. F has to have a Polytime algorithm. So the main job is to come up with an F such that this holds. Okay, so back we go. Okay, so the statement that the restriction that we were just talking about here is up here. In order to show that L1 is Polytime reducible to L0, we have to produce a translation function F. So, just so we know what the job is, we have to produce a translation function F. It inputs a graph G and outputs a propositional logic statement. With the F has to have the property that the graph is three-colorable if and only if the expression is satisfiable, and of course has to be Polytime. Okay, so what is F going to be? So F is going to take in a graph, and F is going to put out propositional logic statements. So you see down here, these are starting to look like propositional logic statements. So where G has vertices V0 through Vn minus 1, then the expression is going to have 3n many Boolean variables, because we're doing three colorability. So A0 through An minus 1, B0 through Bn minus 1, and C0 through Cn minus 1. The idea is that if the ith vertex V gets the first color, then we'll set AI to be T. This is the ith vertex. We set AI to be T, and BI to be F, and CI to be F. If, on the other hand, the ith vertex gets the second color, then we set the associated A variable to be F. We set the associated B variable to be T, and the associated C variable to be F. And finally, if the vertex Vi gets the third color, then Ci gets T, and the other two variables get F. So basically, the A's are lit up when the vertex is color 1. The B's are lit up, made to T, when the vertex is color 2, and the C's are lit up, made to T, when the vertex is color 3. So we just have to write down the conditions for three colorability. So first condition is every vertex gets a color. So for every vertex I, that vertex is either first color or second color or third color, either red or green or blue, or bleen. Okay, and in addition, we have this condition that you're not allowed to have two same colored vertices touching each other. So for each edge, Vi, Vj, we are going to write down some clauses that ensure that the edge does not connect two same colored vertices. So we're not going to have here, if you have the vertex I is connected to vertex J, we're not going to allow both of them to be color A. We're not going to allow vertex I and vertex J to be both color B, and we're not going to allow vertex I and vertex J to be both color C. Now, if you wanted to have vertex I be color A and vertex J be color C, not a problem. But you can't have them both A, you can't have them both B, and you can't have them both C. So we are using propositional logic to express here the conditions that we want on the graph. So we are basically encoding the conditions of three colorability in the propositional logic statement. So of course, we need an example here, and here's the example. So we start out with I just drew a graph that is not too big, not too small, a Goldilocks graph. Here's the propositional logic expression. It's going to have that vertex 0 has to get a color, vertex 1 has to get a color, vertex 2 has to get a color, and vertex 3 has to get a color. Furthermore, there's an edge between vertex 0 and vertex 3. So let's follow this line right here. So I meant to circle this. I'm sorry, I didn't do a very good job. So vertex 0 and vertex 3 has an edge. So the resulting collection of restrictions, there we go, is that it cannot be the case both that vertex 0 and vertex 3 are color A. It cannot be the case both that vertex 0 and vertex 3 are color B. And it cannot be the case that vertex 0 and vertex 3 are color C, as though you didn't get that after the first two. Okay, so basically what we get here is a very large propositional logic expression, not really very large, but large propositional logic expression that encodes the restrictions on the vertices. So it's clear that the graph has a three coloring if and only if E can be satisfied. If the graph has a 3 coloring, then you can satisfy E by taking the associated propositional logic variables to be T or F. So just as a for instance, if this graph has a 3 coloring and it happens to be the case that vertex 0 is color A, why you take A0 to be capital T, to true, B0 to be capital F, and C0 to be capital F, and like that. And so then E is satisfiable if and only if G has a 3 coloring. I think it's also clear, isn't it, that to get from a graph to the expression is doable with a polynomial time translation function. That if you have a graph, in this case with 4 vertices and 4 edges, that you can in polynomial time come up with the associated expression. Okay, of course, if you have a very large graph, you're going to have a very large expression, but a very large graph, when you put it into a polynomial, gives you a very large number. Okay? So completing the proof simply means checking that the translation function, which inputs a bit string representation of G and outputs a bit string representation of S, can be done in polynomial time. There's an algorithm for it that runs in polynomial time. So that all involves checking what is the number of bits in a bit string representation of a graph, and what is the number of bits in a bit string representation of the propositional logic expression. And it's all very intricate, not foolish or anything, but intricate and not especially enlightening, so we're going to pass over it. So this last paragraph here, echoing what we said above, the significance of the reduction is that we now know that if we could solve satisfiability in polynomial time, then we could solve graph colorability in polynomial time. That is, graph colorability is polytime reducible to satisfiability. So if you had a way to solve satisfiability in polytime, then you could take a question in graph colorability, you in polytime translate it to a question in satisfiability, answer it in polytime in satisfiability, and that gives you a total polynomial time answer to your original question. Okay, so once again here, the idea is to produce this translation function to take you from problems of one type to problems of another. And the idea for us, the thing that we're interested in, is that if you could solve the second kind of problem, the problem on the right, if you could solve, in this case, the problem S in polytime, then you could solve the one on the left in polytime. So as a takeaway for why the heck are we doing this, that's why the heck we're doing this. All right, one more example, and then then that's enough for one video. Satisfiability is polytime reducible to Clique. Okay, so we were just talking about satisfiability in the previous example, so we're talking about it again here. And so I want to remind you here that what the Clique problem is. So Clique is the decision problem of the language G, comma B, where G has a clique of at least B vertices. Okay, well, so what's a clique again? So a clique is a set of vertices that are all mutually connected. A set of vertices that are all mutually connected. So if you have, for example, in a graph, get back to my paper. If you have, for example, in a graph, whoops, wrong pen. Then I've drawn a graph that contains, as a subgraph, contains a 4 clique. Okay, so that's a 4 clique. Meaning that this is all 4 vertices that are all related to each other. So if you think of this as, high school friends, these are 4 people who all hang out together. John hangs out with Mary, Mary hangs out with Sue, Sue hangs out with Bob, Bob hangs out with John. They all mutually hang out with each other. Okay, so that's a clique. So the clique problem is to decide if the graph has a clique of at least B vertices. So this graph has a clique of at least 4 vertices, actually equal to 4 vertices. Okay, and the clique is all vertices that are all mutually connected. So we're going to show that satisfiability is polytime reducible to clique. And so, just as a reminder, that seems to be a sort of a thing for folks that they have trouble with. So, just as a reminder, the idea of a clique is, excuse me, the idea of a polytime reduction is that we need to produce an F. So, we need to produce an F. It inputs something from satisfiability. Of course, the members of the satisfiability language are propositional logic expressions, and it outputs something from clique. Right? Clique consists of, it says right up here, clique consists of a pair, graph, comma, bound. And of course, F has to run in polytime, and F has to have the property that E is satisfiable if and only if F of E is in the language L. Okay. So, of course, I'm going to do this with an example again, and there's some parts about polytime that we're not going to worry too much about. So what's the idea then? What do you need to do? Well, we're going to look at a typical propositional logic expression, and we're just going to try to make out what graph do you come up with. Correct. So here's a propositional logic expression, and it happens to have 3 clauses, 1, 2, 3 clauses. You notice, for example, that in this clause there's an x1, but in this clause there's a not x1. So if x1 is true, this clause here won't get to be true by virtue of the x1 part. On the other hand, if x1 is false, this clause won't get to be true by virtue of the x1 part. Okay, so the 3 clauses here have some interaction between them. So in a clause, an atom is either a variable or a negation. So what do you do here? And the answer is, for each occurrence of an atom in a clause, x1 or not x1, x0 or not x0, each occurrence of an atom in a clause, you put a vertex in G. The expression E has 3 clauses with 2 atoms each, so the graph here has 6 vertices. Okay. So the first vertex here, the first 2 vertices here are associated with the first clause, x0 or x1. So this is x0 or x1 is what we're thinking of. In our mind, we're thinking of x0 or x1. Okay. And then the next we're looking at not x0 or not x1. So not x0 or not x1. And then that's this one over here, if I can manage to get over there. So not x0 or not x1. And then the next one is x0 or not x1. So these 2 are associated with x0 or not x1. Okay, so now I think about this here. So connect vertices if the associated atoms are in different clauses. So I don't connect these 2. Never connect these 2. Never connect these 2. As to edge, connect the vertices if the associated atoms are in different clauses and are not negations. Not negations. So I do not connect these 2 because this is x0. This is not x0. This is x0, this is not x0, so do not connect those 2. This is x1, this is not x1. This is x1, this is not x1, so do not connect those 2. On the other hand, this is x0, this is not x1, so do connect them. And this is x1, this is not x0, so do connect them. Okay, now all I got to do is find a 3 clique, and I'm all set. All I got to do is find a 3 clique, and I'm all set. So let me circle here a 3 clique. I have 3 vertices that are mutually related. So the associated is that I want x0 to be true, I want not x1 to be true, and I want not x1 to be true. So we're looking at x0 to be true, and not x1 to be true, and not x1 to be true. I know it's a repeat, but it illustrates that you can have repeats. Okay, by virtue of having those 3 things be true, I managed to satisfy the original expression capital E. And so we're just going to observe that the expression is satisfiable if and only if the graph has a 3-clique, and showing that you can get from the prior page to this page in Polytime. Again, it's not foolish by any stretch of the imagination, but we are representing the satisfiability, we're representing the expressions in some bit string representation. You have to worry about how efficient is that bit string representation. Then we're representing the graph in some bit string representation. How efficient is that? How much time does it take to get from the one to the other? And isn't it clear that you can do this in Polytime? That you could write this in some code. I don't know, maybe it has triply nested loops, so it's big O of n cubed. I don't actually, but it's clearly not exponential. So the fact is that you can run this the translation in Polytime, and that's all we're interested in. So we're not going to worry about the details. Okay, so we've done now 2 different problems, and in both cases we found that that there was, the first problem was Polytime reducible to the second, and in both cases we're going to translate that. We're going to have in our head that has some, and the initial meaning is, we're going to say here, satisfiability is Polytime reducible to Clique, and the significance for us will be that if you could solve Clique in Polytime, then given a problem in SAT, you could translate it in Polytime to Clique, solve it in Polytime in Clique, and so in total have a Polytime answer to SAT. So the interest in translating problems is to use solutions in Clique to solve problems in SAT, ideally in Polytime. Okay, so these Polytime reductions can be intricate, can be very involved, but I hope we've given some flavor of that. But nonetheless, they're useful for expressing how problems are related. In some sense, on this screen, in some sense, Clique is greater than or equal to SAT. In some sense, Clique is harder than or equal hardness to SAT, where you take the definition, of course, to be the definition of Karp reducibility, that Polytime reducibility between the problems. Okay. All right, very good.